Okay, so thank you very much. So here on this slide is a summary of what we discussed in the last 2 lectures. So there was a fairly general story taking as input some category having some nice properties, the most important one being to satisfy this Calabi-Yau-3 condition. And so example of such categories were things coming from derived category of current sheaves on the Calabi-Yau-3 fold, or Fukaya categories of Calabi-Yau-3 fold, or these Calabi-Yau-3 categories attached to quivers with potentials. And given such category and the choice of stability condition, and for every gamma, a kind of topological or numerical class of object, as output of the story, you should get some Donaldson-Thomas invariants, omega, gamma, sigma, which would be integers, which count a stable object where sigma prescribes the stability of class gamma. And the story was reasonably simple when all semi-stable objects were stable. If there are no strictly semi-stable, usual virtual type techniques can be used to define these invariants. But when there exist strictly semi-stable objects, we have to go through some slightly more complicated story. So here just look at this formula downstairs. On the left-hand side, there is some kind of motivic type invariance extracted from the stack of semi-stable objects. And then the suggestion or definition was to rewrite this power series in this exponential form, whose basic structure comes from the quantum logarithm function. In general, it's a conjecture that if you do that, this omega gamma sigma you get is nice, define a polynomial, so that when you get q equal to 1 limit, you get some integer. But we discussed that at least for a quiver with potentials, these integrality conjectures have been proved, first by Meinert-Heinecke and then by Davis-Meinert. And maybe I should mention for like geometric representation theories that actually Davis-Meinert proved some kind of categorification of this statement, which relate on the left-hand side to something called the cohomological Hall algebra of the quiver with potential, with something which on the right-hand side they call the BPS-Lie algebra, which is a categorification of this DT invariant. But for the purpose of these lectures, we'll only care about these numerical invariants. So before coming to a particular story about quiver with potentials, I want to say a few more things about these invariants. So the way we introduce them, we looked at a Calabi-Yau-3 situation because we argue that it's a natural place you expect to be able to count objects, like moduli spaces of expected dimension 0. So it's a natural place where you can get number, where you can do enumerative geometry. Another reason you might care about this number or the Calabi-Yau-3 condition come from theoretical physics. So in theoretical physics, there is this thing called type 2 string series, which live on spacetimes of real 10 dimensions. And in this context, you might care about Calabi-Yau-3 fold because they give you a way starting from 10 real dimensions to cook up a 4-dimensional series. You put your theory on R4 times X, where X is your Calabi-Yau-3 fold, so complex dimension 3, real dimension 6, so that the product R4 times X has total real dimension 10. And then the kind of geometry we were talking yesterday is sheaves on the Calabi-Yau or objects of the Fukaya categories on X. From the 4-dimensional point of view, they look like particles or black holes. And the Donaldson-Thomas invariants we have been talking about in this context can be interpreted as appropriate counts of so-called BPS particles or BPS black holes of a given charge. And one of the reasons I'm mentioning this physics context is some of what we'll do later will be maybe partly motivated by this picture, and at least some terminology has some origin in this picture. So the last part of the general story, the last piece of general theory I want to talk about is the wall crossing formula. So these DT invariants, omega, gamma, sigma, they are counting stable object where the stability is prescribed by this parameter sigma. And as we reviewed last time, the stabilities, let's say in Brillouin sense, naturally form a complex manifold, so a particular topological space, and so you might continuously move in this space of stability conditions. And then you will get some chambers and wall structure. So here I've drawn in red something which are supposed to be of real codimension 1 in the space of stability conditions. And as long as sigma is away from this wall, your integer omega gamma sigma remains constant, does not change. But when you cross one of these real codimension 1 loci, your notion of stability changes in a non-trivial way. Your moduli space becomes different, and your invariant also becomes different. So when you go from one chamber to another crossing a wall, the dt invariance, these integers, might take different values on both sides of the wall. And if you think from a very general point of view, where, like what are equations where walls might happen, they happen when you have two classes, gamma 1 and gamma 2, in your lattice of classes, which are not collinear, they are not proportional in the lattice gamma, but their central charges, or like their stability functions, is complex number z gamma 1 and z gamma 2, which are used to determine the stability. These two complex numbers become parallel. They get the same phase. So generically, if you have gamma 1, gamma 2 not proportional, these two complex numbers have no reason to be proportional. But as some special loci, this complex number will become proportional. They will get the same phase. And then in this case, you can have wall crossing. And it is this condition to have a parallel z gamma 1 and z gamma 2 is a real codimension 1 condition. And so when you cross such a wall, you might ask, how does your set of dt invariants change? And the answer to that is given by some universal wall crossing formula due to Joy-Song and Concevi-Soberman in slightly different languages. And I will review the formulation due to Concevi-Soberman. So to phrase the wall crossing formula, the most important part of the story is a skew-symmetric form. So the origin of this skew-symmetric form is simply the Euler form on the Grothendieck group of your category. So if you have two objects E and F, you can look at the alternated sum of dimensions of X groups between E and F. And because of our properness assumption, X groups are finite dimensional, so this thing makes sense, the bilinear form on your Grothendieck group. And because of the Calabi-Yau 3 condition, because 3 is odd, essentially, this form is skew-symmetric. And so in general, we don't work directly with the Grothendieck group, but we work with this gamma, which is some kind of finite dimensional approximation to it. And we assume that we have something I denote by omega, which is a skew-symmetric form on this lattice gamma, which kind of intertwines with the Euler form. So this skew-symmetric form will be the most important object, actually, for all of the talk today. And once you have this skew-symmetric form omega, you can cook up some natural and simple-looking geometric object. You can define a complex torus T as the spec of an algebra which has a linear basis consisting of monomial x to the gamma, where gamma are in the lattice gamma, and where the product is almost the obvious thing. So the obvious thing will be to consider x to the gamma 1, x to the gamma 2 equal x to the gamma 1 plus gamma 2. You will get the torus whose character lattice is gamma. But because there are signs in DT theory, you need to twist this formula by a sign. So actually, you can check this algebra is still commutative, and in fact, it's isomorphic to the standard algebra of Laurent polynomial linear torus, but not in a canonical way. You need to make some choice to get rid of this sign. Okay, so this thing is just a way to organize the lattice gamma. So again, forgetting this sign, you think of the gamma as a character lattice of a torus C star to the power of the rank of gamma. And then you can think of the skew-symmetric form omega as naturally defining a Poisson bracket on this torus. So you can define the Poisson bracket of the function x to the gamma 1 and x to the gamma 2 on your torus up to a sign. They are given by this skew-symmetric form omega of gamma 1, gamma 2 times x to the gamma 1 plus gamma 2. Okay, so you can just reorganize your lattice gamma with this skew-symmetric form as a torus with a Poisson bracket. And then the wall crossing formula will be stated in terms of elementary automorphisms of this Poisson torus. And these elementary automorphisms will be constructed as follows. So if you fix gamma in your lattice, you can look at the logarithm function applied to x gamma. So by definition, it is this power series sum of n x gamma to the n divided by n squared. It's just a formal power series in gamma. So this thing, you should think about it as in some kind of formal function on your torus. But because you have a Poisson bracket, if you have a function, you can define a vector field. You simply apply your Poisson bracket to your vector field. So it is what is written on the top of the page. I take the Poisson bracket of minus this dialog of x gamma. This thing is a vector field. And then you can formally take the flow at time 1, so the exponential of this vector field, to get some formal automorphism of your torus. And if you work out what it is, this transformation is actually, at the end of this very simple form, it's actually a birational transformation of the torus, sending x to the gamma prime to 1 minus x gamma power omega gamma gamma prime times x to the gamma prime, which is a very simple formula that you might have seen in various contexts, either in the context of cluster algebras or in the context of wall crossing and mirror symmetry, something very much related to Bernd's lectures. So maybe the point of the top of the slide is to explain there is some relation between this simple cluster type looking transformation and the logarithm function, which was somehow secretly appearing when we were trying to define DT invariant. So the relation is that the logarithm function is a Hamiltonian generating this transformation. Yes? And actually, I think actually I mixed my up and down. So here I wrote x to the gamma 1. So x to the gamma are just formal symbols. They're just like formal monomial indexed by gamma. And so yeah, here I should put them up to be compatible. Okay. So they are just monomials on this torus associated to the lattice gamma. And so you might wonder, why am I introducing this torus and why are we introducing these transformations? Is that these torus and these transformations can be used to state the wall crossing formula. And the wall crossing formula is stated as follows. So assume that you fix in the complex plane some strictly convex sector, which is here this cone delimited by these black lines. And each time I have these strictly convex sectors, I can look at the product of the automorphism k gamma to the power of the DT invariance omega gamma. So to each of these red arrows, which are the various values of z gamma inside my cone, so I only look to the gamma such that z gamma, the central charge, this complex number, live inside this cone. So I draw these red arrows to represent these complex numbers. And then for each of these complex numbers, I attach the automorphism k gamma to the power of omega gamma. And then you take the product of this automorphism in the order, let's say you fix some orientation of the plane, let's say in the order defined by strictly increasing phases of your complex numbers. And you might wonder, you might worry that there might be infinitely many arrows in this picture, but because we fix this strictly convex cone, and here if we use this support property we mentioned last time as being part of one of the axioms for the bridge-on stability conditions we consider, it will guarantee that essentially if you truncate this cone at some level, then there will be only finitely many gamma which matters. Then this product will be finite, and then the full product will live in a natural completion, and everything will make sense. Okay, so for a fixed stability, you can draw this picture, and you can look at this product of automorphism to the power of the DT invariance. So it's something cooked up out of the DT invariance. And then the wall crossing formula is a statement that if you cross a wall, you go from one side to the wall to another, then these red arrows will move around because the value of the center charge will move. And some of the center charge can, so on the wall, typically what will happen, some of these red arrows will become parallel. And then on the other side of the wall, they will no longer be parallel. They will just cross each other and become parallel on the wall. So these red arrows will reorganize themselves. And correspondingly, the DT invariance will change. And the statement will be that as long as you look at a collection of red arrows which do not go out of this strictly convex sector, then this product of automorphism to the power of the DT invariance remains constant as formal automorphism of the torus. So we're saying two things defined on two sides of the wall are related. And it's possible to argue that if you know this fact, and if you know all the DT invariants on one side of the wall, so you know this product, then essentially if you factor this product in some other ways, determined by the center charges on the other side of the wall, you can recover all the DT invariants on the other side of the wall. So it's maybe not apparent, but this formula is actually a wall-crossing formula, meaning that if you know all the DT invariants on one side of the wall, you can determine all the DT invariants on the other side.
Can I ask?
Yes?
So in this product, there is finitely many
So in this product, so this product typically will be like, might be sometimes finite, but typically might be infinite. But the claim is that if you do things properly, essentially if you put a bound, like if you look at the gamma such that absolute value of z gamma is less or equal than the constant, then this product will be finite, and it will make sense. And then you can take the limit where these bounds you put on z gamma become bigger and bigger and bigger. So you can work in some kind of completion of this algebra in the x gamma, where you use the kind of modulus of the gamma as a way to regulate and define some completion. And omega gamma has a DT invariance. So if you fix the stability, you have a set of omega gamma, and you use them to define this product. And the non-trivial statement is that if you change the stability, so maybe I should make it clearer to be more compatible, my omega gamma were really omega gamma of sigma. And if I change sigma, this number will change. But the statement of the wall-crossing formula is that this product does not change. And this fact can be used to determine all the invariants on one side of the wall if you know them on the other side.
You fix some sector.
Yeah, and to state it, you need to fix a sector. And somehow you know that for every possible sectors. And this thing, the claim is knowing that is enough. So fixing these sectors is related to this kind of convergence or infinity issue. If everything were finite, you could just forget this sector and just take the product over everything, and there will be no need for this sector. Okay, so this discussion of the wall-crossing formula is essentially the last piece of general theory I wanted to discuss. In the remaining time of today, I want to start talking about something in some way much more concrete. I will talk about the flow tree formula for a quiver DT invariance. So it's a joint work with Yuda Argus, which is a few years old. And as we'll discuss, this flow tree formula is essentially a reorganization of this wall-crossing formula in DT theory. But this reorganization will take some nice shape, which should be useful later, in particular when you want to make contact with Gromov Witten or log Gromov Witten counts of curves. So here I kind of start again from almost the beginning. So QW is a quiver with potential. And I will always note by Q0 the set of vertices and Q1 the set of edges. And here I'm doing some unfortunate switch of notation. I will replace gamma by n for some reason having to do with standard notations n and m in toric geometry. But maybe it's unfortunate because I still denote by small gamma an element in this lattice n. So that you can recognize the small gamma from previously. But in your mind, if you see capital N, you should remember it's a capital gamma from before. So in the context of this query with potential, so this capital N or capital gamma is just z to the power the number of vertices, and you should think about it as being the set of dimension vectors for your quiver representation. If you have a quiver representation, you have vector spaces on the vertices of the quivers, which have various dimensions, and the collections of these dimensions, the dimension vector living inside this lattice. So it's a gamma inside this lattice. And here I recall that in this setup, if you look at the moduli space of all possible quiver representations of dimension gamma, if you look at the modular stack, you simply have a big vector space which comes from parameterizing the linear maps you attach to the arrows, and then we quotient by a big product of general linear groups, which come from the actions on the vector spaces on the vertices. So here I will start doing something a bit different from what we did previously. Previously I was talking about some abstract space of stability conditions, and in the context of query with potentials, I was claiming that okay, if you choose a complex number in the upper half plane for every vertex, you can just build some easy looking stability. And here we will essentially do the same thing, but we'll organize the story in a particular way. So N is our lattice of dimension vector, and I will denote by M the dual lattice, and I will denote by MR the corresponding real vector space. So MR, its arm from N to R, is a set of real valued linear form on N. So it's just a real vector space of dimensions, the number of vertices. And for the story I'm going to describe, I want to see this vector space as being some space of stability parameters or stability conditions. So here is a map from this real vector space to the space of Phrygian stability condition on this Calabi-Yau 3 category attached to the query with potential. If I have an element theta in this real vector space, I will attach to it a special case of the kind of stabilities we discussed previously. So the art will be the kind of standard art given by this category of modules over the Jacobi algebra. So essentially just quiver representations satisfying the relations imposed by W. And I want my Z, my stability function, or my central charge, to be ascending gamma to the complex number minus of theta of gamma plus I times the total dimension of gamma. So what do I mean by that? So gamma live in N, theta live in the dual space M, so theta of gamma makes sense. It's just a linear form applied to a vector. It's a real number. And I take this minus theta of gamma as being the real part of my complex number. And I take the imaginary part to be the total dimension, simply the sum of the dimensions of the dimension vector. So equivalently, I can say the same thing, but since it's Z, send one of the basis vector Ej in the lattice to the complex number minus theta I of Ej plus I. And so the imaginary part is always 1, so all of these numbers are inside the upper half plane, so they satisfy the conditions we described last time. So instead of looking to general element in the upper half plane, I'm restricting myself to the one whose imaginary parts are all 1. And I only remember the real part, which is roughly this theta. Okay, so I will restrict to this real vector space, and I think about it as parameterizing stability conditions, like of this specific kind. And here the further restriction, which from the point of view of the general theory I've been describing is not so natural, but will be much more natural later. If for a given dimension vector gamma in the lattice N, I will only consider stability parameter theta living in the hyperplane gamma perp. So the hyperplane gamma perp is a collection of points theta in MR, so they are all the linear forms on N, which are 0 on gamma. And if gamma is non-zero, this thing is just a hyperplane. And I will always consider theta inside this hyperplane. And if you think what it means for theta to be inside this hyperplane, it means this real part of this central charge or stability function attached to gamma is 0, which means that like the phase of my object is purely imaginary. So restricting to these hyperplanes is restricting ourselves to specific place in the space of stability conditions where this central charge, Z of gamma, has a specific phase. In this case, it's being purely imaginary. And so if you restrict to theta into gamma perp, you can check that the notion of stability kind of simplifies. And to be theta semi-stable, in this case, just means that if V prime is a strict subrepresentation of V, then theta applied to the dimension vector of V prime is less or equal than 0. Okay, so if theta is in gamma perp, it means theta applied to dimension of V, so theta applied to gamma is 0. And now the stability is just saying that theta of dimension of V prime is less or equal than 0. So here is some picture of the standard charge. So if theta is in gamma perp, Z of gamma is always purely imaginary. This is red vertical arrow. And if you want stability, you want sub-object to have like smaller phase. So you want Z of dimension of V prime to look like that. And if you fix such stability theta, then there will be some coarse moduli space of theta semi-stable object, which can be defined by a GIT quotient. And there is a natural trace function on this moduli space of quiver representation defined by the potential. And then in this particular setup, we can give an explicit description of the invariant omega gamma of theta. So omega gamma of theta would just be 0 if there are no theta stable objects. And else, if there are theta stable objects, then the invariant will be some Euler characteristic of this coarse moduli space of theta semi-stable representations valued in some sheaf. And if W were 0, and if the moduli space is smooth of the expected dimensions, this sheaf is just a constant sheaf. And this thing is just the usual topological Euler characteristic of your moduli space. If your space is not smooth, you need to trick. The definition is to use the IC sheaf, intersection cohomology sheaf, instead of the usual constant sheaf. And if W is not 0, you need to apply some vanishing cycle functor to this sheaf, which is what this 5 trace W is. So, okay, at least in this story, there is some relatively short and easy-looking definition. And for most purposes, you should think of this number as being some kind of virtual version of Euler characteristics of moduli space of semi-stable representations. And for the purpose of formulas I'm going to write later, it's convenient to replace these omega theta, which are integers, Donaldson-Thomas invariants, by some rational versions, which I'm denoting by omega bar, and which are related to omega by this kind of 1 over k squared multiple cover formula. And again, the origin of this k squared is this dot logarithm or quantum dot logarithm, which is hidden in this stacky story, like how to count strictly semi-stable. Yes? Sorry, I cannot. Oh, do you mean, yeah, that's right. So the thing is, if it is empty, is it what you are pointing? Yeah, there was a very unfortunate typo. If there is no stable object, you have 0, and not the other way. Yeah, thank you for pointing out. So I'm going to write down formulas involving this omega bar. So the kind of wall crossing type formula we're going to write down will be easier to formulate in terms of this omega bar instead of the omega. There is no loss of information. So if you know all the omegas, so you can calculate all the omega bars. And conversely, if you know all the omega bars, you can recover all the omega by this formula, so, which is an example of the Möbius inversion formula, which is some elementary formula in number theory which tell you how to invert this kind of multiple cover structure. So here is a picture you should have in mind for the remaining time of the talk. So if I care about a Cuvier representation of a dimension gamma, I will always look at the upper plane gamma perp and think of this upper plane gamma perp as a set of stability condition theta for objects for Cuvier representations of dimension gamma. And you could ask, okay, if this thing is a space of stability condition, you can ask, where are the walls? Where could my DT invariant change? And the wall will be exactly the intersections of this upper plane gamma perp with other upper plane gamma 1 perp or gamma 2 perp, such that gamma decompose into a sum of the gamma i's. So here I'm only drawing the simplest example if gamma admit a decomposition into gamma 1 plus gamma 2. So there is an upper plane gamma 1 perp attached to gamma 1, which here I represent in green, which will intersect gamma perp along some codimension 2 locus in the big vector space, like codimension 1 inside each of the upper planes. And if gamma is gamma 1 plus gamma 2, this locus is also the intersection of gamma 2 perp with gamma perp. And the claim will be that this kind of loci, this red locus in this picture, will be an example of place where the DT invariant omega gamma might jump. Another way to describe what's happening is that these upper planes are like the loci. Like gamma perp is a locus where the central charge Z gamma is purely imaginary. So if I'm in the black upper plane, Z gamma is purely imaginary. If I am in the green upper plane, Z gamma 1 is purely imaginary. If I'm in the blue upper plane, Z gamma 2 is purely imaginary. But if I am at the common intersection, they are all purely imaginary together. So all these central charges are parallel, which is a place where wall crossing can happen. And of course, for a given gamma, there might be many ways to write gamma as a sum of other dimension vectors. And so there will be many such intersections with other upper planes. And so there will be, in general, a more complicated wall and chamber structure inside the upper plane gamma perp. So inside each of these chamber, I will have some DT invariance, omega gamma, which is a constant integer. And when I go from one chamber to another, the invariant might change according to the wall crossing formula. So the claim now will be that on this space of stabilities, in this upper plane gamma perp, there is a special point. So not points are equal, there is a special one, which is called the attractor point. So what is this attractor point? So when I was discussing the wall crossing formula, it was important to have this skew symmetric form omega coming from the Calabi 3 structure. And this story of quivers with potentials is omega take a very concrete form. So omega is a skew symmetric form on the lattice n of dimension vector. And it's simply the skew symmetrization of the matrix of the graph. So concretely, omega of the basis vectors ei, ej is just aij, which is the number of arrows from I to j, minus aji, which is the number of arrows from j to I in the opposite direction. So this thing is a very natural skew symmetric matrix encoding the combinatorics of the quiver. And now if I look at the dimension vector gamma, what I can do is to contract this skew symmetric from omega with gamma. So I can try to point out here. So I put gamma in the first entry of omega, and then I view it as a function of the second entry. So here it's some maybe differential geometric notation. I'm looking at the contraction of the 2 form omega with a vector gamma. I get a 1 form. I get an element in the dual vector space. So this thing is an element in M. And actually it is in M, so this thing lives in MR, but actually it is an element in the upper plane gamma perp. Because if you evaluate the linear form on gamma, you get omega of gamma gamma, but omega is skew symmetric, so omega of gamma gamma is 0. So this thing is telling you that you can use the skew symmetric from omega to define a particular point inside the upper plane gamma perp. And I call this point theta gamma, and this point is called the attractor point. And I will call attractor DT invariance the value of the DT invariant at this point. So here is a kind of a picture of the upper plane gamma perp. There are these many chambers, And there is this attractor point represented by a red cross. And what I draw in red here are two chambers which both contain this attractor point, meaning that in any of these chambers, the DT invariant for gamma is equal to the value of the attractor invariant. So I will denote by omega star the value of the attractor invariant for gamma. And some key point is that this notion of attractor point depends on gamma. So it's a bit different from standard stability condition story where people maybe try to find a point in the space of stability, which is like special for all possible gammas. Here, for each gamma, there is a specific point in the upper plane gamma perp. For different gammas, you get different points living in different upper planes. So why do we care about these attractor DT invariants? It's because in many cases, they are remarkably simple. And then they will be used by wall crossing to reconstruct all the other DT invariants. So we'll say that the quiver with potential has trivial attractor DT invariants if these attractor invariants are equal to 1 for like the standard basis dimension vector supported on vertices, and if they are equal to 0 for every other dimension vector which are different from the standard basis vector and which are not in the kernel of the skew symmetric form. So if gamma, so the skew symmetric form omega might have a kernel. It might be degenerate. And if gamma is inside the kernel, then I don't impose any condition. I only impose that these invariants are 0 if gamma is not in the kernel. And then there is some result telling us that actually many quiver with potentials have trivial attractor DT invariants in existence. So you can formulate a result of Bridgeon saying that if your quiver is acyclic, if it does not contain any oriented cycle, in which case W has to be equal to 0, then actually the attractor DT invariants are trivial. And more generally, there is a result of Long-Mu saying that if the quiver with potential admits something called redundant sequence, which is a particular sequence of mutations of the quiver, which is of relevance in some cluster algebra questions. If this condition is satisfied, then it's also true that the attractor DT invariants are trivial. And furthermore, there is some conjecture coming mostly from the theoretical physics literature due to Boja, Mansford-Perlin, and Gromov-Witten, saying that if you care about some geometric context involving some non-compact Calabi-Yau threefold, if X is, for example, a toric Calabi-Yau threefold, then yesterday we mentioned the fact that in such situation, there is a recipe to cook up a quiver with potential which describes the derived category of current sheaves on X. And the conjecture is that if your quiver with potential comes from such construction, if it is describing current sheaves on a toric Calabi-Yau threefold, then it has trivial attractor DT invariants. And the remark is that this conjecture actually is known only in the very few cases, but for example, it is known if X is this local P2 example, this total space of the canonical line bundle of P2, and it's something proved in a paper together with Descombes, Lefloc, Perlin. So in this example, the quiver will look like that, and the potential looks like that.
In general, is that true for quiver with zero potential?
So I think in general, it might not be true. So like if there is no oriented cycle, in which case W equals 0, then it is true. But if you take a quiver with cycles, then and if you put W equals 0, there is no reason for it to be true. And it's one of the reasons why this conjecture is settled is that this statement of having trivial attractor DT invariance is really kind of depend in an essential way on the potential. So if you take this quiver, probably if you take a random potential for this quiver, it will not satisfy this condition. But the claim is that for this particular potential coming from geometry, then the condition is satisfied. So the upshot of this slide is that one reason to care about this attractor DT invariance is that in many interesting examples, they're essentially trivial. They're like 0 or 1, and understood, including cases which are geometrically interesting.
Question?
Yes?
Could you say why this attractor point lies on the wall?
So it does not have to lie on a wall. So here on the picture, I made it lie on the wall. So it's just a way to draw the picture. It just, if you think about what it looks like, you will realize that it tends to be on the wall. It's like, yeah, maybe you should, yeah. So yeah, in general, it could be anywhere. I just happen to draw the picture like that. Okay, so one reason to care about these attractor DT invariants is that they are really simple. But not only they are really simple, but they can be used to reconstruct the general DT invariants. And the reason for that is you can just apply the wall crossing formula. If you know the attractor invariant, it's just some invariance for a particular stability point, and so you can just apply the wall crossing formula from any other stability to get your invariance. And if you do that, you get a formula you will get, which will have the following shape. So I fix gamma, and I fix theta inside the hyperplane gamma perp. So here is my starting point. I want to know what happens here at this stability point. And then, so this picture is really what you should look at to understand this formula. So you want to understand the DT invariance here. And the nice thing you should try to do, you should try to move towards the attractor point for gamma. So here the attractor point for gamma, I've drawn it in blue here. It is some other point in gamma perp. And starting from theta, you can just try to move straight in the direction of the attractor point. And if you can just move there without crossing any wall, then you are done. It just means your DT invariance is equal to the attractor DT invariant. But maybe along the way you try to move, you will hit a wall, like here. And then when you apply the wall crossing formula, it will tell us that some object of class gamma become unstable, but there are some other sigma infiltrations. They are made of stable objects of class gamma 1 and gamma 2 for some decomposition of gamma into gamma 1 plus gamma 2. So the wall crossing formula will tell you if you know the DT invariance for gamma 1 near this point and for gamma 2, then you could reconstruct what happens for gamma. So now the question is what happens for gamma 1? And then you iterate the argument. In gamma 1, you try to go toward the attractor point for gamma 1. And if at some point you hit a wall corresponding to a decomposition of gamma 1 into gamma 3, gamma 4, gamma 5, then you will apply the wall crossing formula. You will need to find the invariant on the other side, and you continue. And so at the end of the day, you get a formula which actually is only correct for this rational invariance, saying that this rational DT invariance omega gamma is the sum of all possible ways to split gamma 1 into gamma 1 plus gamma r, some interesting factor depending on gamma 1, gamma r, and then the product of the attractor invariance for gamma 1 and gamma r. And according to this picture, this coefficient, this interesting number, has a natural decomposition according to all the pictures like that. And these pictures like that are essentially trees embedded inside the real vector space MR. And these trees have natural rational direction, and there is a natural balancing at each vertex coming from this decomposition at the vertices. And so this tree is essentially a picture of a tropical curve in the real vector space MR. Yes?
It's perpendicular to where your attractor point is. What if you hit a wall and then you go perpendicular, or it cannot happen?
Sorry?
When you hit a wall and you have to move towards the attractor point, what if you're moving in a plane parallel to the wall to the plane where the attractor point is?
Yeah, I think yeah, so the claim is that this thing somehow, yeah, it's pretty a good question. The claim is it will never happen. So the direction in which you really move to go to that structure point, you need to go in this direction, like contraction of gamma with omega. And the kind of thing we're describing will only happen if, like, essentially omega of gamma 1 with gamma 2 will be 0, I think. And in this case, there is no wall crossing anyway, because the wall crossing will be controlled by this form. So if there is a non-trivial wall crossing happening, it means it's possible to continue. You are never, like, inside this codimension 2 join of the hyperplanes. So this thing is a kind of first key picture, is that if you try to calculate your DT invariant for stability parameter theta, you might try to move in your space of stability in this kind of way. Each time you try to move towards your attractor point for your class gamma, but if in the meantime you hit a wall, then your gamma split, and then you try to move into the attractor points in these other upper planes for other gamma i's, and then you iterate. So you get this kind of universal formula reconstructing DT invariant in terms of the attractor DT invariant with some coefficients having to do with these trees.
So is it plain that if you follow these structural curves, this kind of branching process, that you always end up at some point?
Yeah, that's right. The claim is that after some point you just continue straight. And maybe in this setup is actually not really mysterious because there are only finitely many ways to split a dimension vector. Because for Quiver representations, a dimension vector is just a collection of non-negative integers. So there are finitely many possible decompositions. So for fixed gamma, there are finitely many possible branching.
But then you also end up on these gamma I curves, which has their own attractor points.
Yeah, but these gamma I are kind of smaller. For example, the total dimension is, yeah, that's right. So indeed, this kind of a question, you will need to address it if you try to do something similar in a kind of geometric context. Then this type of question will be much more tricky to address. But here, because everything is made of non-negative integers, you can use that to argue that at every step, like essentially something decreases. And the process is finite for every fixed gamma. So the main goal for the remaining time of this talk is to describe the so-called flow tree formula. So this iteration of the wall crossing formula tell you there exists these coefficients which are indexed by these embedded trees of these tropical curves. And these coefficients, they are just numbers, like rational numbers. And in general, these rational numbers are complicated numbers. And what we'll be discussing is a formula expressing these rational numbers in a somehow explicit way. And the formula, which was conjectured by Alexander Pierrick in the physics literature. And this formula and this tree story is a kind of toy model of something which in the physics literature is called the attractor mechanism for black holes in 4-dimensional supergravity. It is where the name attractor originates in the physics literature of the 90s. And this quiver story is a kind of toy model for it. And so Alexander Pierrick had some conjecture for these quiver toy models. And what we did in this paper with Julia I advertised at the beginning is provide a proof of this formula. And the proof will simply involve starting with this picture and then modifying or perturbing it a little bit. So the main reason why this picture is complicated is the fact that the vertices of this tree might be more than trivalent. They could have any possible valency, which are related to the fact that you look to the decomposition of your vectors into any sum of other vectors. And so we'll do something which is quite familiar in the context of tropical geometry or tropical curve counting. We'll try to perturb or modify this picture to reduce to some trivalent graph story. But in the original picture, there is not enough space to perturb. So what we need to do is to consider a higher space. So if I fix a vectors gamma 1, gamma r, summing to gamma, and if my goal is to find a formula for this coefficient fr theta of gamma 1, gamma r, which appear in this kind of universal formula, what I will do is I will consider some lattice curly n, which is r-dimensional. So I will introduce a basis vector f1 to fr for this bigger lattice madcal n. And I will consider the obvious projection map from madcal n to straight n, sending fi to gamma I. So the basic issue is that this gamma 1, gamma r, they have no reason to be linearly independent. For example, there might be repetitions, like gamma 1 could be equal to gamma 2. So here what we do is just we introduce the formal vectors fi, which replace the gamma I, but now are kind of linearly independent. We just consider lattice z to the power r, we just project to n. And if you think about what it means on the dual side it will be mapped in the other direction. The vector space MR, where our stability parameters are living, will be mapped to a kind of bigger space, madcal MR, which is a dual of this madcal n. And our point theta will map to some point that are denoted by alpha of theta in this higher space. So what you should think about here, what we are doing, is that because this madcal n in general is bigger than this lattice n, in the dual picture we'll embed the previous picture, where this picture is living, into a higher dimensional real vector space. And there will be enough space to perturb the picture. So I will describe the perturbation in one moment. What we will do is to perturb this point, alpha of theta. So we want to perturb this parameter inside the hyperplane sum of I fi perp, which is like the natural lift of gamma perp. So you consider a generic small perturbation theta tilde of this point, but now in this higher dimensional vector space. And the claim is that once you make such a choice, there will be a formula for the coefficient you care about, which was a flow tree formula conjecture by physicists, which write your coefficient as a sum of binary trees. So this thing is a combinatorial formula. It no longer involves tropical curves, graph embedded in a space. It just involves some of the abstract graphs. And these graphs are trees, and they are just binary trees. So every vertex is trivalent. There is a root, which is represented here. And then there is a vertex below the root, and afterwards, every such vertex has two descendant vertices. And these trees have R leaves. And I decorate these leaves by the basis vectors f1, f2 to fr. And once I have such binary tree whose leaves are decorated by this vector f1 to f2 to fr, I can decorate any vertex v inside my tree by some vector fv by deciding that if v prime and v double prime as a descendant of this vertex, I define fv as being fv prime plus fv double prime. In other words, at the roots, I know what happens at f1, f2, and then if the two legs come together to a vertex here, I will assign f1 plus f2, and so on for all the vertices. So now for every vertex v, I know how to attach a vector fv to it. And now the contribution of this tree in our formula will be a product over the vertices of this tree. And the contribution will be essentially the skew symmetric form applied to the vector fv prime and fv double prime, where v prime and v double prime are the two descendants of the vertex v. So essentially at every vertex, there is a trivalent-like picture, and you just use a skew symmetric form to attach a number to this trivalent vertex. And you take the product over the vertices. Up to some details I have not discussed, which is in red here, which is some epsilon. And all the difficulty will come from this epsilon. So this epsilon will be either +1, -1, or 0. And it is where the dependence on the stability parameter theta will be introduced. So what is this epsilon? So here I wrote down some formula. So this formula may be not so important. So Actually, I think in the coming exercise sessions, Julia probably will go through an explicit example of applying this formula, and you will see what it does in some concrete example. So these formula are defining for each vertex v some epsilon v. And to define this epsilon v, we first assign to every vertex v some point theta tilde v in this higher dimensional vector space MR. And we do that, so the reason it's called a flow is that it's really analog to the picture I was describing previously. You start at the root of your tree, and at the root of the tree you define this theta tilde to be your original stability parameter theta tilde. And then if you know what happens for the parent P of V of a vertex V, so the vertex above your vertex V, there will be a formula to tell you what is theta tilde V for this vertex. So here is some formula. And if you think about what this formula is, it's really telling you start at theta tilde P of V, move straight towards the attractor point, and at some point you will hit a wall. And the position of this intersection point with the wall will be given by this formula. So that way, so there is a kind of iterative definition of a parameter theta tilde V for every vertex V in your tree. And then once you know all these parameters theta tilde V, there is a formula for this epsilon. So this epsilon is a sum of two signs. So this sign is easy, just the signs of the skew symmetric form. And here the sign of this point theta tilde of the parent of the vertex V applied to the vector f of v prime, where v prime is a descendant of v. So it's a maybe slightly complicated but fully explicit formula. And there is actually something tricky to argue, which is the reason for this perturbation business, which is if you take the sign of something, you need to be sure that this thing is non-zero, else the formula will be ambiguous. And the claim is that if this initial parameter theta tilde is a generic enough perturbation, then when you go through the iterative definition of this parameter theta tilde, these quantities which appear here, they are always non-zero, and so the sign is well defined. It's +1 or -1. So here are a lot of formulas. There's a picture you should remember is a picture which is down here. So in black is the original space MR. And in this MR, I have this tree starting from the point theta. And this tree, like here, is not trivalent. This edge here is split into three others. So I have a 4-valent vertex in this black tree. And what we are doing by introducing this bigger space, we might call MR. So now there's a bigger space. And in this bigger space, what happens is a kind of common intersection of all of these black rays lift to some loci, which are this green line, which becomes different. And so if instead of starting with the point theta, I start with the point theta tilde in this bigger space and try to follow the same flow story, at every intersection with the wall, only decomposition into pair of vectors will be relevant. And so I will only get this kind of trivalent. So here what's happening is this red thing is really like two different graphs. So I have one here splitting into two, and then I have another one going straight and splitting into two later on. So this red non-trivalent curve in this bigger space kind of decompose into two 3-valent red curves. And essentially the proof is roughly this picture to do this perturbation and argue that when everything is generic enough, the general trees get perturbed into binary trees. And the whole trickiness is to work out that this formula for the signs is correct to get this abstract combinatorial formula. And some of these signs, epsilon, have to do, if you want to think about them, where they come from, they have to do with the realizability of your tree, of your abstract tree, as a tropical curve in this picture.
Can you repeat again why the tree is trivalent? So the formula that makes trivalent because it makes computation easier?
Yeah, that's right. So the point will be that in this formula, the contribution of a tree will be simply the product over the vertices of something very simple. which only use a kind of trivalent structure as a vertex. Whereas if you have a complicated non-trivalent tree, there will be a global contribution of this tree, which is something complicated.
And you know that you can always deform. This is part of
Yeah, so this thing is part of the theorem that if you say that tilde is generic enough, then if you do the deform story, then it will be automatically made of trivalent things. And so this discussion is quite parallel to some story happening for tropical curves. For example, if you read the paper of Bernd and Nishinu on tropical correspondence theorem, there will be something very close to that happening. And it's not a coincidence, so the kind of conclusion for today is that starting from quiver GT invariants and moving appropriately in the space of stability conditions, we got these tree pictures, which are essentially tropical curves. And so from there, you might ask, do these tropical curves are the tropicalization of some actual geometric complex curves somewhere? And this thing will be what we will be discussing next time, how to lift this picture. So there is essentially these two pictures, this picture involving this higher valence vertex, or this picture involving this perturbed trivalent vertex. You can ask, can you lift any of this picture to a picture about honest complex count of curves somewhere, which in some tropical limit will reproduce this combinatorial picture. And so we'll discuss that next time on Thursday. That's all for today. Thank you.